Hello everyone. Today we will do the experiment on 1-bit and 2-bit comparator, that is the magnitude comparator using logic gate. So this is the virtual laboratory website where we can see the aim is written, and this virtual laboratory is sponsored or created by IIT Roorkee. So and this link is here. So it is like that to analyze the truth table of 1-bit comparator using NOT, and NOR logic gates, ICs, and 2-bit comparator by using 1 input NOT, 3 input and 2 input and 3 input OR and 2 input exclusive NOR logic gates IC, and to understand the working of 1-bit magnitude comparator and 2-bit magnitude comparator with the help of arity display. So let us move to its theory portion. So magnitude comparator basically compares the magnitude of a binary number. Suppose there is a two numbers A and B. This is say two numbers A and B, and there are three possible outcomes. First is A may be greater than B. Second, A is equal to B, and third is A less than B. These are the three possible output after comparison, after magnitude comparison of two numbers A and B. So coming to the truth table of 1-bit magnitude comparator. So here you can see in the figure 2, that is the truth table of 1-bit magnitude comparator. So two inputs are there, A and B. A is A and B. These are the two numbers having 1 bit each, and there are three possible outputs. So first column, as far as outputs are concerned, is A less than B. Second one is A is equal to B. Third one is A greater than B. So, and input combinations, suppose in first case A is 0, B is also 0. So you can see A and B both are 0, 0. It means both numbers are equal. That is why the column where A is equal to B is given, output is 1. So this output is 1 here. Then 0, 1, it means A is 0, B is 1. In that case, B is greater than 1. That is why column A less than B is 1. Then third case, A is 1, B is 0. So here you can say A is greater than B. That is why the last column is 1. And if both A and B are 1, 1, 1, 1, it means both numbers are equal. That is why the middle column A is equal to B is 1. So this is how 1-bit magnitude comparator's truth table can be derived. Now accordingly we can write the expression, Boolean expression. So first column A is less than B. So we can see here it is mentioned A is greater than B. I think this is the third column. Sorry, this is third column. So here you can see when A is 1 and B is 0, then it is A is greater than B. So A, B bar. This one. A less than B means A bar, B, and A is equal to B means A bar, B bar plus AB. So now these are the Boolean expressions of all three outputs. After that, accordingly, we can implement the circuit. So here two inputs are there, A and B, in the figure 3, logic circuit of 1-bit comparator. So for A is less than B, the upper gate is giving the output, and lower one is A is greater than B. And final output is A is equal to B. In this case, you will get the output. So the logic which is expressed here is implemented with the help of circuit. So Boolean expression has been implemented with this circuit. So you can see here B, and here it will come B bar. And after that, I think, let me increase the size. This gate is NAND gate we are using. NAND gate, and below is also NAND gate, and this is NOR gate. So through that they are making this circuit. Now coming on the 2-bit magnitude comparator, let us see the truth table. So 2-bit magnitude comparator means there are two numbers, A0, A1. This is first number. Second number is B0, B1. These are the two numbers having 2-bit each. So this is the input and output. Again, three kinds of output. First is A is less than B. Second one is A is equal to B. And third one is A greater than B. So in 2-bit magnitude comparator, you can see total input becomes here 4-bit. So straightforward, we can write all the possible combinations with the help of 4-bit, like 0, 0, 0, 0, then 0, 0, 0, 1, and lastly 1, 1, 1, 1. So it becomes very easy to write all possible combinations when we consider all inputs as a this 4-bit number. However, these are 2-bit number basically each. Then based on the truth table, based on the input, we can write down the respective outputs. Suppose when is A is less than B. So you can see for the first case, when A number 0, 0, B is also 0, 0. So the middle column, that is A is equal to B, is 1. Rest are 0, 0, because only middle column, that is A is equal to B, that is the true. Otherwise, all two are false. Now 0, 0, when A is 0, A1 is 0, 0, and another number is 0, 1. So you can see here B is greater than A. So that is why first column is giving 1 and rest are 0, 0, and so on. So it becomes easier to write the truth table. And after that, write down the expressions, these Boolean expressions of all three outputs, like A is less than B, A is equal to B, A is greater than B. So wherever we have logic 1, at that place, what is the input combination that we have to write? Similarly, for A is equal to B and A is greater than B. So this is the expression. So for A is equal to B, you can see this can be realized with the help of exclusive NOR gate. And rest are A is greater than B and A is less than B. And the circuit implementation is shown here. For A is less than B, for A is equal to B, and A is greater than B. So you can see exclusive NOR gate and then putting here AND gate, because this 2-bit number has to be compared. If both are equal, then only A is equal to B will be 1. So applications is written here. Application of comparator, that is magnitude comparator, are used in central processing unit, that is CPU and microcontrollers. These are used in control applications in which the binary numbers representing physical variables such as temperature, position, etc. are compared with the reference value. Comparators are also used as process controller and for servo motor control, and used in passive password verification and biometric application, because unless password matches, then only your system opens. So for this checks equality. So that is how this magnitude comparator becomes very important circuit. Now let us go to this pretext. This is theory. Now pretext is all the comparison made by comparator is done using, say, circuit. How many circuit? One circuit. One that is not the outcomes of magnitude comparator is A is greater than B. Okay, A minus B, not correct. A less than B is okay. A is equal to B is also okay. So A minus B is not okay. If two numbers are not equal, then binary variable will be. If two numbers are not equal, then binary variable will be 0, because they checked equality for particular case which is being asked here. Which one is a basic comparator? And XOR, NAND, exclusive NOR gate is the basic comparator for equality. Comparators are used in memory, motherboard, CPU, and hardware. Just we have seen that in the CPU. So let us check. So fortunately, all answers are correct here. So this is the pretext quiz, which we have done before going for experiment. Next one is the procedure for the experiment. So it is mentioned here. First step is the switch on the power supply button to supply 5 voltage to the circuit. Then step 2 is the press switch 1 for input A and switch 2 for input B. Switch is in on when this green signal is shown, and off when red signal is shown. Step 3, when the input A is greater than the input B, LED 1 lights up. When the input A is lesser than the input B, let us see this one. This is not become a problem. However, you people can read. Okay, so let us coming for simulation. So simulation circuit, we will do first 1-bit comparator so that we can understand, because it is simpler than 2-bit. So you can see, you can click here to see the instruction again. Minimize it. Now in order to supply, so we have used here 3 ICs 7404, that is the hex NOT gate or inverter. So there are 6 NOT gate, and another IC is 7408, that is the quad and gate, these 4 AND gates, and here 7402, that is the NOR gate has been used here. So as it should be exclusive NOR. Okay, let us see how it is working. So first VCC is given to 14 number pin in all ICs, and 7 number pin is given to ground here. And after that, this is the connection. We can see switch the A, that is the A, and switch 2, that is the B. So A, B, 1-bit number. So A and B, these are the 2 input. And this is the power supply, just on. Click here, you will make it on. Off. So it is not off. Okay, once it is on, after that here these switches are used to give the input, say logic 0 or logic 1, and these are the 3 outputs shown as LED. So A is greater than B, the LED 1, A is less than B, so LED 2, and A is equal to B, then LED 3. And the connections you can go through. Let us check. These connections are basically implementation of A is greater than B, that is nothing but A B bar. So for A B bar, here we can get, see, this is the A signal. A is given to this in NOT gate input, and from here we can get A bar. So this is A and this is A bar, and these inputs are given to the another logic gates. And here B is pin number 3. From here we can get B, and B bar from pin number 4. So this is how all 4 possible input combinations can be taken from pin number 1, 2, 3, 4. So of NOT gate. Now let us see the combination. Suppose both are 0, 0. So if both are 0, 0 means this LED 3, that is A is equal to B, should be 1. So let us check that. So you can see here serial number 1, A is 1, B is 1. So for the output, A is greater than B is 0, A is less than B is 0. However, A is equal to B is equal to 1, because both number are equal. Now I will make, suppose this A is equal to 0 and B is equal to 1. So here A is equal to 0, B is equal to 1. You can see here B is greater than A. So that is why you can see where B is greater than A is 1. Then go for 1 and then 0. So for 1, 0, 1, 0. So A is greater than B and rest. And after that, both are 0, 0. So, and so both are 0, 0. Again, A is equal to B. So all 4 possible combinations we have taken 0, 0, 0, 1, 1, 0, 1, 1. And we got this truth table. So this is how we can see the outputs of comparator circuit. So from here we can print. Okay, so either in PDF form or you can take actual print also. From here you can see. Okay, this print you can take, because this is the circuit diagram. Now once it is done, let us move to simulator 2. Simulator 2 is about the circuit implementation, which we have seen in the breadboard type or actual IC. Now this is the circuit diagram. So here we just take the input, suppose 0, 0. So we know both inputs are equal. Then what shall be the output here? So A is less than 0, false. A is equal to B, yes. A is less than 0, false. And now check. So you can find here, this is the correct. So this will use as a verification truth table. So suppose A is 1 and B is 0. So what will happen? It means A is greater than B. So where is A is greater than B? Third one. So we can write here 1 and rest are 0 and check our answer. So we can see here the second one is also correct. Now let me do mistake. Okay. So I will make this 1 also and this I with 1. Okay, and if I tell that A is less than B, although A and B both are 1, 1 means both are equal, but I am deliberately making the mistake. So suppose A is less than 1, this combination, and rest I am making 0. So let us check. So you can say this is incorrect. So 1, 1 should be what? A is good. A is equal to B. The rest should be 0. Now check for the same input. Now it is correct. So in this way we can check all 4 input combinations and find out the outputs. So this is how 1-bit magnitude comparator circuit can be done. Now go for the post test. Once we have completed the experiment, we can check our knowledge. The purpose of a digital comparator is to convert analog input to digital, no. To create different outputs, no. To add a set of different numbers, no. To compare a set of variables or unknown numbers, yes. So it is comparators. A magnitude comparator is defined as a digital comparator which has only one output terminals, two output terminals, three output terminals, no output terminals. So we have seen just there were 3 output terminals, is less than B, is equal to B, or A greater than B. Now, if a comparator, in a comparator, if we get input as A greater than B, then output will be 1, okay, or 0 either. But here we, in a comparator, we get input as, then the output will be, if it is equality, then it will be 0. Otherwise, it is 1. Then we have to see what is the, for time being, I am putting here 1. Then output will be. How many inputs are required for a digital comparator? So how many inputs? Minimum 2 inputs are required to compare. So an identify comparator is defined as digital comparator which has only 1 output terminal, 2 output terminal, 3 output terminal. Identify. So I think it will be 1. Let us check. So fortunately all are correct here. So 3 output. Okay, so in a comparator means this was giving output 1. So this is the post, and then some reference books are mentioned here. Okay, so in this way, 1-bit magnitude comparator we have done. Later on, you can give the feedback. How do you feel about this? So this is also necessary. So let us move to now 2-bit comparator, if it is there. So theory, procedure, if it is 1-bit, this 2-bit simulation, go for 2-bit magnitude comparator, which is given in our syllabus. So again here 2-bit comparator means 2-bit inputs are there, A0, A1, and B0, B1. Earlier only 1-bit, now it is a 2-bit. So circuit becomes a little bit complicated because it requires now 16 input combinations, and then 16 input combination makes circuit complex little bit. However, we can make circuit, no problem, so far as tables are concerned. So here we will give all input combinations, like suppose all are 0, 0, 0. So you can see in all 0, 0, it means A is equal to B. So let us check this one. But before that, we have to on this power supply. Give the power supply. Now inputs are all 0, 0, 0 here. And add, so you can see A is equal to B, this one. And after that, 0, 0, 0, 1. This is the first combination. And so you can see 0, 0, 0, 1 means B number is greater than A. So B number is greater than A means this column will be logic 1. Let us check. So here you can see A is greater than B. Then 0, 0, 1, 0. This is 2. Add it and find out this. Then 0, 0, 1, 1. This is 3. So you can see B is greater than 1. So you can see B is greater than 1. And then this is 1 and rest are 0. So now A is greater than B. So add. So you can see A is greater than B. This is the output. Then 0, 1, 0, 1. So now equal. So both number are equal. So you can see for equality condition, this is 1. And in this way, all 16 combinations you should fill up. Okay, let me put 6, then 0, 1, 0, 1. 0, 1, 0, 1. So G. So let us make all. This is 4, 0, 1, 0, 0. Okay. Then 5. This is 1. Then 6, 1, 0. Then 7. Then 8. Add and see the number. Then 9. Add and see the table. Then 10, 1, 0, 1, 0. Then 11, 1. Then 12. This. Then 13, 0, 1. Then 14. This one, and then 15, all 1. This will be equal. So here we have covered now all combinations. So some are repeating here, that is why total 18 is are coming. So in this way we can do the experiment. Here simulation 2 we go. So this is a circuit here, all possible input combinations here we can make. Let us see here. So this will be suppose 0, 0, 0, 0. Circuit is there. You can see this is the circuit diagram. I have clicked. You people can take the circuit diagram image. Then here you check, verify basically. Both are 0, 0. It means both are equal. And then I put here 0 and I put here 0 and check. You can see this is the correct. Then this is a 2-bit number. So 0, 1, and I also take this one 0, 1. So you can see again this is equal. So this is also correct. So you can put all input combinations, all 16 input combinations with the help of these 2-bit number and verify. As I told you, you can see that this is circuit implementation. Okay. So A0, A1, B0, B1. These are the inputs and these are the NAND and gate or gate implementation. So instructions are given here. You can read the instruction. And after that, let us check what next is there. Post test. So I think same thing are given here. We can do. We have already done. So this is how we are able to complete this 1-bit and 2-bit magnitude comparator in your syllabus. Exactly 2-bit magnitude comparator is there. So more importantly, you have to complete this 2-bit magnitude comparator. So this simulation one. Okay, 1-bit magnitude comparator is for your basic understanding purpose, and 2-bit, this is one, and 2-bit one is for compulsory, as because this 2-bit magnitude comparator, the circuit we can see here. We can take the print of the circuit from here and try to put into your notebook. This is the circuit. So once we understand the logic, there is no difficulty in putting the circuit into breadboard. So in this way, we are able to complete this experiment. Thank you so much for attending this laboratory. So please submit after completing this experiment. Please submit in our Google Classroom. Thank you.